Limited, Chennai in 2012. As a member of board of governors NIT Puducherry in 2012 to 15. As a head Department of Electrical Engineering IIT Madras 2010 to 2013. She has published more than 49 journal papers and several patents on her name. She has won award in Maharashtra State Government Society Scholarship for Talent Development in Mathematics and Physics in 1975-78. She got second prize at the colloquium for the young physicist, Indian Physical Society, Calcutta in 1985. Also got the IEEE Distinguished Service Award in 2019 by the Institute of Smart Structures and Systems for distinguished and seminal scientific and technical contributions to the growth of microsystems technologies in the country. Thank you very much.
So we welcome Dr. Bhattacharya here for the third session. Over to you, ma'am, for the session.
Yes, thank you very much for your kind introduction. I'm going to start my presentation now. Let me just share the screen. Is it visible?
Yes, ma'am, it is visible, but it is not in presentation mode.
Yeah, I'm just going to presentation mode. Last time I did this, there was a problem. Just let me know if it is gone.
Yeah.
Is it presentation mode now?
No, not yet.
Well, it should have come by now. It is in presentation.
No, ma'am, not yet.
Yeah, so there is a bug. I noticed this even last time. But in Google Meet, somehow it's not going into presentation mode. It is presentation mode here.
Acha, at your end, it is in presentation mode?
Yes.
Okay. So maybe some issue. But it is okay. We can read the things like.
Is it?
Yeah, it is okay.
But animations don't work if it's not.
Yeah, animation will not work in this mode. That is the.
I don't know why this is happening. I should get this checked.
Okay.
No, na?
No.
It hasn't come even now.
No, not yet.
Okay. Anyway, I will remain in presentation mode here and hope that the animations work. Okay, hello everybody.
Okay.
My talk is on silicon-based biosensors and bio-MEMS and a little bit of NEMS. I think really we have not exploited even MEMS to its full extent. But anyway, sometimes we even have to go to nanometer scale to improve sensitivities, etc. So I'll start by talking on introducing a specific biosensor, and that is for triglyceride. And we'll talk. Actually, I'm going to talk about two different classes of biosensors here. One is an electrochemical biosensor, and that is the EIS cap. It's an electrolyte insulator semiconductor capacitor. I'm also going to talk about a mechanical biosensor, and that is the micro cantilever. So even for the EIS cap, which starts off as a normal sized biosensor, we do use micro-MEMS techniques to miniaturize the sensor, and that also improves performance. And towards the end, if we have time, I'm going to talk a little bit about silicon nanoporous membrane. That's what I'm working on at present for the last 2-3 years on the fabrication. And it's not really a sensor, but it is used more for, it has applications in dialysis and things like that. Okay, so on top is a schematic for general bio analysis. Just 1 minute, there's too much noise outside. Hey, Chinnu, hey, noise coming, Pandugo. Hey, noise coming. Sorry about that. Yes. So on top, I have on top I have a schematic for transducer. So on the left you see the analyte. That is what we are trying to estimate or detect. A biosensor. Yes. Yes.
Ma'am, slides not move, ma'am. Slides will not move, ma'am. Okay.
Slide is also not moved. Oh,
Yes,
then
yes.
I can't be in this mode then. Nothing is working in this. Okay,
Now it's moving. Now it's moving.
yeah, because now I'm out of this screen, full screen mode.
Oh.
So I was hoping that maybe it will start working at some point. Really. Okay, so this slide also you wouldn't have seen, no? The triglyceride, EIS cap, etc. Okay, this is a schematic. So we start with the bioanalyte. It can be a chemical or a biochemical analyte that we are trying to detect. A biosensor necessarily has to have a bioreceptor. The bioreceptor can be an enzyme, can be a cell, can be an antibody, antigen system, and so on. It is an ongoing list. Then comes the transducer, where we come in. That is the device that is going to transform the signal coming from the bioreceptor into a measurable signal, which can be electrical or optical. Of course, we prefer electrical because it's easier to play around with amplify the signal or give a feedback, whatever you want. So the transducer itself, the first one is the electric that I just mentioned. It could be thermal. It could be a change in pH, which we can directly measure using a pH meter. It could also be optical. All of you have seen this advertisement of the glucose sensor, which once upon a time was in Akram. That the detection is optical. The reaction is enzymatic, so that the bioreceptor is an enzyme, but the detection it used to be a change in color. It is color and that is optical. However, as I just mentioned, we are more interested in the measurable signal being electrical in nature. In electrical, you can again have a current signal, a capacitance signal, or a charge which causes a change in potential. And each of this is possible. Whichever would be the easiest is what would be opted for. So why silicon? Why silicon for biosensors and MEMS? We already know that silicon, thanks to the integrated circuits and many devices, is very well-known material. It's the most studied material in the periodic table. But for biosensors and MEMS, it turns out that it's also an excellent material for semiconductor sensors. Because it is silicon, it should be possible to integrate with the circuit, because now, silicon technology is in tens of nanometers. So we really don't need that for sensors, but what we need, if we are talking about MEMS, is in micrometers. So as you can see, it's like orders of magnitude greater than what is available now, state of the art. So therefore, miniaturization is very much possible with very few errors, and this increases both sensitivity as well as, because it's small, we can make arrays of sensors and get multiple outputs from the same die. The cost of silicon material cost is still quite high, but the reason that we can get away with it is, if you look at the performance to cost ratio, that is also high. So silicon is not a passive material. It is to be used as an active material. And so even though the cost is high, because of the high performance, this is still viable. And why is the cost high? Whenever I give a talk on MEMS, this is what I spend a lot of time on. It is because silicon, it is possible to do batch processing. So even though silicon material is high, process cost individually is high, because you can process many wafers at the same time. That's why it's called as a batch processing. And each wafer can have, depending on the size of the circuit or the size of the sensor or the device, you can have anything from few thousands to few millions in per wafer, and there you are at a time processing 100 to 200 wafers. That is in commercial fabs. Of course, in labs, we still work with few wafers, 2-3 wafers at a time. That is more than enough. So we all know that silicon has excellent electronic properties, material properties. As it turns out, like a bonus, when people started working on silicon for MEMS, it has excellent mechanical properties, right? And what do I mean by that? There's a cliche. There's a saying that it is harder than steel and lighter than aluminium. And it is true. It's actually, its yield strength is higher than stainless steel and its density is less than aluminium. And you can go back and check the numbers if you don't believe me. In addition, silicon can be modified to meet high precision and reliability. What do I mean by this? I don't always have to work only with single crystal silicon, which is expensive. I can work with other forms of silicon like polysilicon or porous silicon. I can grow oxide. It's very easy to grow silicon oxide. It's a very stable compound. I can grow silicon nitride, deposit silicon nitride, which again is a very stable material. So just the family of silicon and all the associated compounds and forms of silicon gives us a big box to take out things from and make new sensors and actuators. Okay, so next, as I said, as a prototype, I'm going to talk about triglyceride sensor. So let's learn a little bit of what are triglycerides. I saw that you are a mixed batch, my audience, and I don't know about you, but when we were students, we didn't learn any biology. So it's important to understand what we're doing, and I learned a lot of bio. Of course, I had a very good collaborator from biotech, but I had to learn to understand what is going on. Okay, so triglycerides, anyone who's above 40 probably has gone for blood tests, and they measure what is called as the lipid profile. The cholesterol profile in blood has HDL, LDL, triglycerides, and of course the total cholesterol. So an excess of triglyceride in our blood indicates, is indicative of coming on cardiac problems. Okay, so that's why you have to keep it in check. So triglycerides cause coronary vascular diseases, and therefore is a biomarker for these diseases. And that is why we need to test it. It's present, naturally present in food. So it's there in our blood, and we may have to control the amount of triglycerides that is going in if anyone has excess triglyceride. Therefore, if we make a triglyceride sensor, it has applications both in clinical as well as in food areas. The way we will do this sensing is, so again on the top, I have a shorter form of the schematic I showed you in the first slide, that is bioanalyte, and then it was bioreceptor. So in this case, we are going to use an enzyme as the bioreceptor. The reason is, if you attend a talk on sensors and sleep through the entire talk, you can wake up in the end and ask 3 very relevant questions. What are those 3 questions? What is the sensitivity? Always important. What is the selectivity? Most important. Because anything that works in the lab, when you take it in the field, it doesn't work, right? Because there are so many other things there. So it has to be very specific. And of course, cost. Cost is also important, because when we are talking about sensors, etc., we are thinking of a market, and unless it's viable in terms of cost, nobody will take it up. Okay, so we need the enzyme to make it selective or specific. So what happens in the presence of the enzyme? The bioanalyte hydrolyzes. Hydrolysis is nothing but an reaction with water, but it would react with water only when the enzyme is present. In other words, the enzyme is a catalyst. So the enzyme allows the hydrolysis of the bioanalyte, and usually this hydrolysis produces either an acid or a base. Okay, therefore, this acid or base can cause a change in the electrolyte, or in the reaction. Because of the reaction, there's some change which the transducer needs to pick up and make it a measurable signal. So as I mentioned when I started the talk, I'm going to talk about 2 different kinds of transducer. One is electrochemical, and that is the electrolyte, insulator, semiconductor, capacitor, called EIS cap. The other one is mechanical. It's just a cantilever beam. A cantilever beam is a beam which is fixed at one end and free at the other. We are talking about micro cantilevers because the dimensions will be in tens and hundreds of micrometer. Okay, so moving on, I first start with the EIS cap. And on the left is the EIS cap is a very simple device, right? We are making it with silicon. It's a capacitor, therefore it's a two-port or two-terminal device. So the silicon, we usually make it of P-type silicon, and that is the gray part. By the way, can you see the marker, the pointer I'm using? Can you see that? Hello?
Yes, madam.
Okay. So this gray part here is the silicon. And then is the insulator. We actually use a stack of insulators, oxide followed by nitride. The arrows have moved because I suddenly decided to increase the size of the figure. Okay, the lower part is oxide and on top of that is nitride. And I'll tell you the reason for doing this. I mentioned that silicon, one advantage of silicon is it's very easy to form oxides on it. Oxide can grow on silicon if you expose silicon to either oxygen or water vapor, steam, and yeah, somebody's talking? Okay, never mind. And the interface between silicon and silicon dioxide is very good, very clean. You know, our whole MOS and MOSFET integrated circuit, silicon IC is dominated by MOSFETs, MOSFET-based CMOS, NMOS, etc. logics, and all that. The gate oxide is always silicon dioxide. So the interface between silicon and silicon dioxide is very good. But silicon dioxide has a problem. It is porous by nature. And since in the electrolyte insulator semiconductor capacitor, it's a very harsh environment. The insulator is being exposed to the electrolyte, usually water-based electrolyte. So you can imagine all our ICs, we do so much packaging on them so that they never see the ambient conditions. So if oxide by its very nature is porous, and therefore if we just expose the oxide to the electrolyte directly, the electrolyte, the liquid in the electrolyte or the ions can penetrate through the pores and reach the interface. And that is not very good because it makes the interface unstable. The device parameters are going to change, and so that is to be avoided. And that is the reason we cover the oxide with a nitride layer. Nitride has to be deposited. I have written it as Si3N4, that is stoichiometric. In practice, the way we deposit it by chemical vapor deposition, it will be SiXNY, where X and Y are less than 3 and 4. Right? So, why silicon nitride? Because silicon nitride, it turns out, is a very robust dielectric. It's a robust dielectric, so it doesn't allow this liquid or the water in the electrolyte to penetrate and reach the insulator semiconductor interface. Okay, in fact, silicon nitride is what we use as the final layer for most integrated circuits before packaging because it's a very good protective layer. So next question you may ask is then why who bother about the oxide at all? We could just deposit nitride directly on the silicon. Okay, that is not an option because I just spent a few minutes talking about the interface. The interface is very important. If you have a large number of defect states between the oxide, between the semiconductor and the insulator, that also affects the characteristics of the capacitor, right? So that's why we have stacked oxide and nitride. Oxide is right on top of silicon to ensure that the interface is very good. Nitride is deposited on the oxide to ensure that the insulator that faces the electrolyte is robust enough that the characteristics don't change. Okay, so that is a simple device. The top is the electrolyte, which is held in this picture. It is held in a Teflon cell. The cylinder column-like thing holds the electrolyte. I mean, it can be KCl, NaCl, anything. Mostly we use KCl, salt solution. Capacitor has two contacts. Top contact, we use a platinum electrode, platinum wire dipped in the electrolyte. Electrolyte, of course, is conducting. Probably many of you know. So if I look at a KCl solution, what? It will have K plus and Cl minus. Not very different from semiconductors having electrons and holes. Except instead of conductivity due to electrons or holes, in KCl we'll have conductivity due to K plus or Cl minus. So very similar to semiconductors. So capacitor will have two contacts. At the back of the silicon, we make an ohmic contact. This is p-type silicon. So depositing aluminium, which is group 3, we can easily make an ohmic contact. This is our device. So this is a schematic of the device now. So I have the device below with the bioreceptor. And right now, I haven't introduced any bioreceptor. I just told you about the device. So I still have to introduce the bioreceptor. But there is a bioreceptor and the bioanalyte comes in. So if it is, this bioreceptor is the enzyme and triglyceride comes in, an acid gets produced, the pH changes and it affects the electrical output. In this case, we will measure the capacitance voltage characteristic. At the bottom is an actual photograph of this device. You can see the Teflon cell and the silicon. Here it ends in aluminium. In practice, we put that silicon wafer on a stainless steel plate. Right? And we take the bottom contact from the stainless steel plate. You can see these screws here. And the top contact is platinum wire dipped from the top. There's a through hole at the top. Okay, since I have a mixed background, I'm going to start with a little bit of basics on the device. What is an EIS cap? It is very similar to a metal oxide semiconductor capacitor. By the way, a MOS cap is the basis of all MOSFETs. So anyone who has done a devices course would be very familiar with it. Please bear with me. Just 2 slides. This is so that everyone else is familiar with what we are talking about. Now, don't get alarmed by this MOS cap and EIS cap, etc. It's really a parallel plate capacitor. All of you have done parallel plate capacitor in school itself. And remember, what is the parallel plate capacitor? If I have 2 plates with a dielectric in between or even air in between, the capacitance is given by epsilon A by D. Epsilon is the permittivity of the dielectric or air. A is the area of the capacitor and D is the gap between the capacitor plates. That's all you need to know. Except if it's a MOSFET or a EIS cap, the capacitor is not fixed like the formula I gave you, and we have to see what it is like. So a typical MOS cap, again p-type silicon, and this green is the oxide layer, on top of which is the metal MOS cap. So MOS, and then we can apply different biases and measure the capacitance. Do remember that for capacitance measurement, we always have to apply an AC voltage. Capacitance measurement cannot be done with DC. So the bias applied is DC, but superpose on that a small AC, and this frequency as well as the magnitude is very small, but this frequency is also important. So when I go from MOS cap to EIS cap, everything else is same. P-type, again, because I have a stacked oxide, a stacked insulator, I have 2 layers here, and the metal is replaced by a liquid given by these dashes, and now I have the EIS cap. Okay, so the metal of the MOS is replaced by an electrolyte to go from a MOS cap to an EIS cap. Okay, now what happens to a MOS capacitor as I change the voltage? So I said it's a p-type, right? Remember, so p-type has a large number of holes which are positively charged, a large number of free holes. So let us say, now don't worry too much about this flat band voltage, let us assume that is 0. Okay, so I call the top metal as gate, and if I apply a voltage there which is less than 0, that means this is negative. Metal has a negative charge. What will happen? It will induce negative charge in the metal plate. Now obviously there are negative charges here. It's going to attract positive charges on the other side of the dielectric, which is the semiconductor. No problem, because it's p-type semiconductor. It has a large number of free holes, and therefore they'll get attracted to the insulator semiconductor interface, right? What is this? This is your standard parallel plate capacitor, right? This is called as accumulation. Why? Because the free holes are accumulating near the insulator, near the oxide. And the capacitance is simply given by epsilon A by D, the formula I just gave you for the parallel plate capacitor, because it's like a parallel plate capacitor. So let's look at the CV characteristics on the right. I have capacitance on the y-axis and voltage Vg, the applied bias, on the x-axis. I told you that whatever this flat band voltage is zero, right? So as long as the voltage applied is negative, the capacitance will remain constant at what we call as the oxide capacitance, because this is decided only by the oxide thickness. Okay, so far so good, simple. Now let me change the voltage on the metal plate. So in the metal plate now, I am applying Vg greater than 0. Voltage is positive now. Therefore, the charge induced in the metal plate is positive. I can do that, just like a parallel plate capacitor, but I get into trouble on the semiconductor side because it is p-type. So the number of free electrons is negligible, right? So I cannot have the negative charge induced on the other side of the oxide using electrons. But first thing that will happen because of the field that is generated by the applied bias is that it's going to repel all the electrons, all the holes from in the semiconductor from close to the insulator. Okay, so I have positive charge on one side of the oxide. On the other side of the oxide, because I need negative charge there, the first thing that happens is it pushes all the holes away from the interface. Now, what is left behind is the negatively charged acceptors, right? The holes, each hole is connected to, has come from an acceptor dopant, right? These acceptor dopants are all ionized and each has contributed a hole which is free in the valence band. Now, if the free holes have moved away, then since the dopant atoms are bonded, they're substitutional donors, acceptors, so they are bonded to the silicon atoms, they cannot move away and they have lost their free hole, so they are negatively charged. So I have this is called as the depletion region. The word depletion comes because it is depleted of all the free carriers, holes in this case, leaving behind what is also called as space charge layer. Space charge due to the charged acceptor atoms. So now if you look at this picture, what does the capacitance look like? Of course, I still have the oxide capacitance, but I also have a depletion layer capacitance, right? Because this is no free charge. So this also will behave like a dielectric. So it's like having two capacitors in series, and if two capacitors are connected in series, then the effective capacitance is 1 by C1 plus 1 by C2. So as a result of that, the net capacitance falls. This is what you see here in the ideal picture. So as long as negative charges are induced into the metal and free holes can compensate that on the semiconductor side, the capacitance remains constant and is called as accumulation. Once you change the polarity and I need negative charge on the semiconductor side, I don't have free electrons, so the holes get repelled, and it is the depletion region charge that compensates the positive charge on the other side of the oxide. And now since I have two capacitors connected in series, this will keep falling. And you can imagine if I keep increasing Vg, I need more and more negative charge. So what will happen? The depletion layer bit will increase more and more and net capacitance will decrease more and more. For people who are familiar with devices, beyond a certain point, I hit inversion, but I'm not going to introduce that here because all we need is the most important region for us to use this as a sensor is the depletion region. So we are interested in the depletion region. Now, I said this flat band voltage, let's assume it is 0. This flat band voltage is indicative of that when I put the device together, metal oxide semiconductor or electrolyte oxide semiconductor, I'm assuming that the bands are flat at 0 applied voltage. That means there is no exchange of charge between the metal and the semiconductor even at 0 applied voltage. It is an ideal case. In practice, there are so many non-idealities. The most common non-ideality is the metal work function, which is a measure of the metal Fermi level, or the metal Fermi level is a measure of the metal work function, it's very unlikely that that will have the same value as the semiconductor Fermi level. Therefore, when we put them together, there will be some field, there will be some exchange of charge, right? And the effect of this, that is called the flat band voltage. So now I have to apply a bias to get into flat band condition. So the effect of flat band voltage is actually just a parallel shift in the CV characteristic. So I showed you the ideal one first. If flat band voltage is non-zero, it can be positive or it can be negative. In this case, it looks like it is negative. There is just a parallel shift in the CV characteristics. Okay, so this was a recap of metal oxide semiconductor capacitor. What happens in the case of EIS cap? And I have a schematic on the right-hand side top corner. I have used the oxide as the insulator. This is not a nitride. In the next slide, I'll also show you the picture of the nitride. It's simpler to understand this with oxide. Okay, so if you look at the oxide, so what I have here, this is the oxide. The silicon is somewhere here. I have not shown the silicon. I'm just showing the interface between the oxide, which is the insulator, and the electrolyte. Now, you know, oxide, what is the formula? It is SiO2, right? Now, at the interface, clearly I have terminated the oxide, correct? So I have all these SiO bonds sticking out. Now, depending on the pH of the electrolyte, and if you remember your high school chemistry, what is pH? If a liquid is acidic, it has pH less than 7. If it is basic, it has pH greater than 7, right? So the pH, in other words, for acidic material is a measure of the number of hydrogen ions available. Okay, now this electrolyte, I'm going to define a zero charge pH for the electrolyte. And this zero charge is not pH equal to 7. How much is the zero charge pH will depend on what the electrolyte is, what the electrolyte is, what the insulator is. So let's say it has some value, zero charge. What happens at that value of pH for the electrolyte is that there's just enough hydrogen ions present in the electrolyte so that an SiOH is the hydroxyl. So SiOH gets formed and SiOH is neutral because the hydrogen H plus has compensated for the O minus and now this SiOH is neutral. That's why it's called zero charge. If my electrolyte is at this pH, there is no charge at the interface between the oxide and the electrolyte. If the electrolyte has a pH which is greater than zero charge, what does it mean? It means it's more basic now. And more basic means fewer hydrogen ions. So I don't have enough hydrogen ions. So this SiO remains as an unpassivated bond with a negative charge. If on the other hand, the pH is more acidic than the zero charge pH, I have plenty of hydrogens and therefore it's possible that two hydrogen ions bond to the SiO and I end up having SiH2 with a positive sign. So remember, same insulator, in this case oxide, same electrolyte, same in the sense that if it's KCl, same concentration KCl, let us say. But if I vary the pH, and I can vary pH of KCl by adding traces of HCl or NaOH bases and acids. So just by changing the pH, I can change the charge at the interface. It can be electrically neutral at zero charge pH. It can be negatively charged. If it is more basic than zero charge, it can be positively charged if it is less. Okay, so depending upon the pH of the solution, I can get an interface which is positively charged, negatively charged, or neutral. And this is almost like applying a VG, positive VG, negative VG, or VG equal to 0 at the metal gate of the MOS. Okay, now what is the effect of that? So the effect of this, of course, will be that the flat band voltage will change depending on the pH. A very analogous situation is if the metal work function changes. As the metal work function changes, the flat band voltage can change. Similarly, as the pH of the electrolyte changes, the flat band voltage of an EIS cap system can change. Now, if I measure capacitance voltage curves, the CV curve will shift as the pH changes. And that is the principle of the EIS cap for pH measurement. Okay, I've also here shown you the picture of nitride. Now, when it is nitride, it is that what I had shown as SiO now becomes SiNH. SiNH2 happens at zero charge, it is electrically neutral. If it is less than zero charge, then I end up getting SiNH minus. One hydrogen is missing. If I have lots of hydrogen, I can end up getting SiNH3 plus. So I have an extra hydrogen here, making it positively charged. NH2 is electrically neutral. NH minus with just one hydrogen is negatively charged. Okay. Now here is this was first proposed in 1987 in a paper in IEEE Transactions, and Harame et al. They proposed a new device which was called as ISFET or NFET, which was insulator semiconductor filtered transistor. NFET was with enzyme to use as a biosensor. Okay, so the expression for the flat band voltage is the phi SI, etc., are very similar to what we have for the case of MOS, but here what is important is you have a factor potential that depends on the pH, right? So the flat band voltage depends on the pH of the electrolyte. Okay, so now if you plot CV characteristics on the right, these are actual experimentally measured values, and we varied the pH from 3.5 to about 10, so very large variation in pH, and you can see that the CV curve shifts. This is for p-type. The CV curve shifts from right to left as the solution becomes more and more acidic, right? So pH 3.5 is at the extreme left, and pH 10 is at the 9.98 is at the extreme right. So it behaves as we expected it to behave, but to quantify it, at the middle of the depletion region, we dropped a perpendicular, and at the voltage we call as U bias. When you plot U bias as a function of pH, we get a straight line plot. The sensitivity of this pH meter is given by the slope, which typically is 55 millivolts per unit change in pH. If you work out the theory of the interface and for oxide or for nitride, this is for nitride, the theoretical limit, this is called as Nernst response, the theoretical limit is about 59 millivolts per unit change in pH. So experimentally, of course, your surfaces may not be as good as expected in theory. So 55 to 57 is very good. It's very rare to get 59. Okay, now I have a good pH sensor. How do I convert the EIS cap into a biosensor? Okay, so for the triglyceride sensor, I told you that triglycerides, and here I'm using tributylene, which is a short chain triglyceride, as a prototype for our initial experiments. So this tributylene, in the presence of the enzyme lipase, reacts with water, and the reaction products are glycerol and butyric acid. Glycerol you're all familiar with, dense viscous liquid, but we are now interested in the butyric acid. So since it forms an acid, there's a change in pH in the electrolyte, and that causes a flat band change, and therefore it will cause the CV curve to shift. So we have checked out our device, a sensor, with enzyme lipase and with tributylene, which is a short chain triglyceride. Now this is where I need the animation. Basically what it shows, this is just a cartoon that my PhD student had made when he was presenting. So this represents the enzyme. It's not like a test tube, it's actually a big molecule, and all the interaction happens at the surface. So what he was trying to show is what happens is when the enzyme comes in contact with the triglyceride. So lipase, this is tributylene. It comes and forms a complex. So this picture, of course, has all three. So this green is the tributylene, which is formed a complex with the enzyme. And finally, the reaction takes place, and these two dots are the reaction products, right? So tributylene forms a complex with the enzyme lipase, and then butyric acid and glycerol are the reaction products. Why is it specific? Because, for example, if you're testing triglyceride in blood will have many other things, right? It may have sugar, it will have cholesterol, all other kinds of things. So you can see there are 4 different shapes. And if I could show you the animation, it would show that when either of these 3 come, they don't form a complex. Okay? The only thing is this blue, which forms a complex here, and that's how the reaction takes place. Okay, now as you can make out, this is a very interdisciplinary, multidisciplinary area. We are talking about devices which are in either electrical engineering or in physics, and we are talking about biosensors. A lot of this is biochemistry in chemistry department or biotechnology department. So we need to get anyone who is going to do interdisciplinary work must get their terminology straight. So a biotechnologist or a biochemist will call the tributylene or the triglyceride as a substrate. What is our substrate? In electrical engineering in devices, substrate is silicon or glass, whatever is the base for the devices. So here, please, that's why I wanted to point this out, that here the substrate is the bioanalyte, which is tributylene. So what this reaction indicates is the enzyme and the substrate form first a complex, ES, then the reaction takes place, so it takes finite time, and at the end of it we get the product. In this case we get 2 products, glycerol and butyric acid. The enzyme remains as it is because the enzyme is a catalyst, so it helps in the reaction and then it comes back. So you can really use it again and again. Of course, what happens is after multiple use, the activity of the enzyme goes down and you need to replace it. Since I've been talking about triglycerides all this time, I thought I'll introduce another bioanalyte, and that is urea. And you know, excess of urea in our blood, it is an indicator of renal kidney problems. Okay, and also urea is a very common adulterant in milk, so one needs to check. So sensor for urea will be very useful for both checking for adulteration in the dairy industry as well as in the health industry. Okay, now what happens in urea? Again, this is the formula of urea. In the presence of the enzyme urease, it undergoes hydrolysis, which is reaction with water, and it produces ammonia, NH3, and carbon dioxide. The plus sign seems to have gone off. Okay, now both ammonia and carbon dioxide are soluble in water. As you know, carbon dioxide is not very soluble. You know, soda is made only with under pressure. Normal pressure, it's not very soluble. Anyway, but both are soluble. This is ammonia is quite soluble in water. So what happens? Carbon dioxide, when it dissolves in water, it forms carbonic acid. Ammonia forms ammonium hydroxide. Ammonium hydroxide is a very strong base. First of all, carbon dioxide doesn't dissolve that well in water, and secondly, it's a very weak acid, carbonic. So the overall change in this case is ammonium hydroxide. So the pH increases. I wanted to give you this example because in the first case for triglyceride, butyric acid is formed. That's a weak acid, but that's the only acid that is formed. So it changes the pH of the solution. For urea, the enzymatic hydrolysis creates a strong base, and that changes the pH towards basic. That is, it increases the pH. Okay, I'm going quite slow. I started at 3:30, it's already 4:12. I should hurry up. So these are the calibration plots, which was U bias as a function of concentration. Known amounts of tributylene was done. CV plot was generated. U bias was measured from CV plot. And of course, since in the case of urea, it becomes more basic, the slope is in this direction. For acidic, the slope is in this direction. Now, Another thing that usually people prefer for sensors is to have a linear response. It's not that critical, but somehow it's easier to calibrate, etc., when there is a linear response. So as you can see, there's a linear response over a fairly large range, 0.15 to 20 millimolar in the case of triglyceride, tributylene, and 0.2 to 20 millimolar. Now, one thing to note is that it flattens out at the two ends. When the concentration is high, we see that the sensor is not responding, and even though I have not given the points here, actually even on this side, it kind of flattens. You can see there's a little change in slope, and eventually it flattens out. So both at high and low concentrations, it becomes non-linear. It kind of flattens out. And what is the reason for that? At high concentration, it's not worrying, because usually we use these sensors only to measure low concentrations. What happens at high concentration is the amount of enzyme we have put in is not enough. Enzymes are expensive, and we have optimized the amount of enzyme. So for the enzyme that we've used in these experiments, it is not, that complex it forms, E plus S, right? If the enzyme is not enough, then it's going to get saturated with whatever tributylene is there. Increasing amount of tributylene is not going to give you more signal. Okay, so this can be easily remedied. I can just increase the amount of enzyme. I'm not that worried about this, but I'm more worried about the lower concentration. Why is the sensor not responding at lower concentrations? Now, the electrolyte that we use has KCl, as I told you. It has the bioanalyte, it has the enzyme. That's how the reaction takes place. And what I did not tell you is it also contains a buffer. Usually we use phosphate buffer. And the reason we use a buffer is enzymes are like prima donnas. Prima donnas are singers. Everything has to be exactly correct. Otherwise they're not able to sing. So enzymes also, unless the conditions are perfect, enzyme will not act. So the enzyme needs the correct pH, needs the correct temperature, only then it will work. That is the reason we have to use a buffer. Now again, high school chemistry, what is the work of the buffer? The buffer ensures that the pH remains constant. So even if I use a dilute buffer, right, when I have the reaction, some of the change in the pH because of the hydrolysis, enzymatic hydrolysis, is compensated by the buffer. It doesn't matter when the concentration is high. When the concentration is low, whether it is tributylene or urea, the change in pH is so small that the buffer just neutralizes the change. Correct? So this is a measurement artifact, not a device limitation. This is a measurement artifact. So we should use as small a buffer concentration as possible. If you don't use buffer, we tried that also. It's an electronic measurement. And we found the measurement was too noisy. So that was not an option. And I think we used half molar or 1 molar buffer concentration. Okay, so please remember that in EIS cap then, it is difficult to measure very low concentration. However, this linear range is adequate for most measurements. In clinical range, this falls well within the clinical range. So it's really not a problem. Okay, so we used this device to measure triglyceride concentration in blood serum. And so all this has been done after clearance from Institute Ethics Committee. You cannot report on any human samples, even taking data from humans, you need clearance from Ethics Committee. And so we took blood samples from volunteers, and serum was converted into serum. Half of it stayed with the pathology lab in our hospital, half of it we brought back to our labs. And the first column is the measurements in milligram per ml from the patho lab. Then we brought it to our lab and measured the shift in U bias and the triglyceride concentration here. And as you can see, there's very little difference. I call this error. It's actually the difference percentage, because I don't know if the error is on their side or on our side, but the agreement is very good. Maximum is 7.7%. So it works. It works for blood. We also measured urea in blood samples following the same protocol. Urea, mostly agreement was not bad, but one of the samples, the error was 25%. That is quite large. We also measured in urea levels in milk, and that agreed quite well. Okay, so this was the biosensor made of silicon. Now we come to MEMS, and we want to miniaturize the EIS cap. Why? Because smaller dimensions, scaling it down to micrometer range, reduces the volume of the bioanalyte. Earlier we were taking 10 ml, and then in the lab we were using 2 ml of the serum. Now you might say, I don't care, you take 10 ml of my blood, right? But it's not just the blood sample. If I have a large amount of the analyte, I also need large amount of the reagents. Everything is expensive. I told you enzyme is very expensive. So the advantage of miniaturization is that I save not just in collecting sample, but also in all the additional reagents we use, and the reactions are now faster. I'm using smaller volumes, so my throughput also increases. So by miniaturization, I could reduce the volume from few milliliters to 0.1 microliters. And I must address a point of caution here. You can miniaturize from 0.1 microliter, which is 100 nanoliters. I could make it 10 nanoliters. I could make it 1 nanoliter, right? But you should not miniaturize just for the heck of miniaturization. If I use such a small sample volume, it might just evaporate before you've done any measurements, right? So one must always keep in mind that what is your application, how long does it take to do the measurement. For example, this the enzymatic hydrolysis takes a finite time. Formation of the complex, right? That has to be optimized. So it cannot be too fast. So therefore, my sample must last through that measurement. And that's what, these are all design parameters when you design your device. Okay, so since now we are going to replace the Teflon cell with the silicon microreactor. That is etching silicon, I can form a microreactor within the silicon itself, and therefore batch processing is possible. Not only that, I can, because it's very small, I can make multiple EIS caps on the single die, and in principle, we can measure many bioanalytes simultaneously, though we actually just stayed with triglyceride. Okay, so this is these are the process steps. What we do is silicon bulk micromachining, etch it in KOH, and we make this micro well. I think you have several lectures on processing, and you'll hear more about that. So I'll quickly go through this. After doing the etching, we make the oxide and deposit the nitride, grow the oxide and deposit the nitride. And these large orange things are the isolation between. So each of these small wells is a microreactor, and the reaction can take place. Okay. So these are the details of the substrate, same P-type 100 substrate. We earlier, for the larger devices, we were using normal thermal oxidation, but now if the size reduces, if the lateral size reduces, even the vertical dimensions have to reduce. So we had to use much thinner oxide. Earlier we were using about 100 nanometers. Now we are using 10 nanometer oxide. So we use rapid thermal oxidation for that. And silicon nitride, we use the same process but reduce. Earlier we were using 70 to 80 nanometers. Now it is 30 nanometer. Now in this device, see, so far we were talking only about this part, which is the lower part. We went one more step, and we bonded the silicon wafer to a glass wafer with through holes on which we deposited. So you can't stick a platinum wire, right? When you're doing measurements in a miniaturized device. To do measurements in the lab, you can. But if you are planning to commercialize the device, then sticking a loose wire would be problematic. So we decided to put the silver electrode, the top electrode, was embedded in the structure. So it was deposited on this top glass plate, and we filled the electrode right up to here. Okay, all right. So this is now, miniaturization. In my first slide on miniaturization, I only told you the advantages of miniaturization. Okay, we also came across new problems when we miniaturized. And one of them I've shown here. What we found was, when we miniaturized and we first tested using a platinum wire, using a gold wire, and we found that even at the same electrode, same bioanalyte concentration, there was a drift in the CV plot. And the drift is quite a lot. It was with platinum wire, the drift in 10 minutes was about 300 millivolts. With gold, it was even worse, 650 millivolts. And what is the reason for that? Remember, I told you that for capacitance voltage measurements, you apply the CV. This V is DC. But to make capacitance measurements, we always have to use an AC voltage. And for an AC, the insulator is not an open circuit. For DC, of course, the oxide and the nitride would be an open circuit. But for the AC, it is not an open circuit. It will have an impedance depending on the thickness as well as the frequency of measurement. Now, what happens is with the reduced dielectric thickness, the capacitive impedance goes down, right? Because it goes as 1 upon omega C, which is inversely proportional to the thickness, parallel plate capacitor. So that increased the AC current density. And why did we use platinum? Platinum is supposed to be totally unreactive, even more than gold. That's why we were using platinum electrode, and we never had a problem for our larger devices. But now with the smaller devices, it was enough to create that current was enough to oxidize or make the platinum react. This is called as polarization reaction. And of course, if we had talked to an electrochemist, they would have told us that. We talked to them, of course, after we had the problem, and they suggested silver chloride electrodes. And as you can see, compared to 600, the shift here in 10 minutes was just 0.66 millivolts. There is still a little drift, but it is really negligible compared to the other two materials. So this was a problem in miniaturization that we faced and we solved. Okay, so finally, of course, the test of the pudding is in its eating. So after putting all this together and filling it with the electrolyte, this is the capacitance voltage measurement. And now we are getting, as we saw for the larger EIS caps. So therefore, this packaging kind of works. So by the way, we used, for bonding the glass with the silicon, we used an adhesive bonding, and we used photoresist because photoresist is used quite often in semiconductor technology, and it does not leave much residue. Oh, and to add, the sample size now is increased to 20 microliter. It is still much less than 2 milliliters, which is the sample size for the large EIS caps, but it is much greater than just for this part. And that is important. That ensures that there's always a reservoir and this doesn't evaporate during the measurement. So that was done by design. Okay, now so far we were mixing the bioanalyte, triglyceride or tributylate and the lipase separately for the reaction. Now, if this were to get commercialized, then the more number of steps the operator has to do, chances of error are more. So instead of that, we decided to fix or immobilize the enzyme lipase on the surface of the triglyceride, on the surface of the nitride. So here you see, at the nitride, we mixed enzyme and tributylate. If I also immobilize the enzyme, all that I have to add is the sample, which is the tributylate. So we developed the protocol, and I'm not going to go into that. It's called a silanization with glutaraldehyde and enzyme. What is important is this is a covalent immobilization. What is immobilization? As the name suggests, you're trying to put the enzyme onto the surface of the nitride. Now I can make a mixture and put a drop and let it dry. That is also immobilization. But that is called as physical adsorption or physical immobilization. What will happen? Sometimes it will scatter, the drop will scatter more, sometimes it will scatter less, and therefore there will be inconsistency or irreproducibility. That is why we prefer covalent, and hence all these steps. A covalent bond is a very strong bond. Once we have covalently immobilized the enzyme, you can actually wash it. You can wash it in water to remove all the physically adsorbed enzyme, and only enzyme that will remain is what is covalently bonded. So it is very reproducible, and we can check that this has happened by doing FTIR measurement or some other. There are a lot of spectroscopic measurements by which you can verify that this is the case. So finally, this is our biochip, triglyceride biochip. We do batch processing till the glutaraldehyde step. After that, we dice out the each individual dye and do the photoresist bonding, and we always leave the enzyme immobilization as the last step, because remember I said that it's very touchy. So once you immobilize it, you want to start using it for your experiments. Okay, so this is a schematic now. Below is the silicon, and here I've added these black dots are the enzymes. On top is the glass wafer with the through hole. You can see the silver chloride electrode here, and it is to be filled to this level to make contact with the silver chloride. The active area of the device is always full, right? As long as you use it so that this area, which is the capacitance area, remains constant. On the right is the photograph of a device. So since we have the silver chloride layer here, this is the silver chloride layer. There's through hole, and inside you can see the silicon chip which has the EIS cap. We also developed a readout circuit, direct readout, because you can't carry a whole capacitance voltage measurement bridge for the measurement. So we developed a readout circuit, and the principle of the readout circuit is measuring capacitance is not easy. That's why you need a bridge and all that. What we did was we put the EIS cap in what is called as a relaxation oscillator, and as the capacitance change, the frequency of the measuring frequency, you just need a timer circuit. That is very easy. So we converted variation in capacitance to variation in frequency, and there is this paper. You can look at this paper for anyone who's more interested in the circuit part. Okay, so first we developed the pH readout circuit. So here is the pH readout circuit with the display, and the idea is that this will be the readout circuit, this will be the chip, silicon biochip, and as you can see, we also measure the pH using a standard pH meter, and the agreement is very good between the readout system and the pH meter. So that worked. So next, I wanted readout meter for my blood triglyceride. Okay, so before that, we need to generate the standard plot, which is equivalent of the calibration plot which we're using for the pH. I'm not going to use the pH U-bias plot now, because I'm not going to measure U-bias. I'm not measuring the whole CV plot. So I have to generate a standard plot, and that will decide that what is the time of the measurement that we need, etc. So what the inset gives is that we have, for a given amount of tributylene, which is 0.5 millimolar, which lies well within the range of clinical measurement, I use different amounts of enzymes and look at the reaction rate. So as you see in the plot, the amount of enzyme increases as I go down. If the enzyme concentration is very high, the hydrolysis reaction is very fast, right? The x-axis is time. So pH is changing very fast. If the amount of enzyme is very small, so 0.5 millimolar, there's no change at all. It's almost flat. Because, so I need both enzyme and substrate, which is tributylene, for the reaction to take place. So we should choose an amount where the reaction is neither too fast, not too slow, and I have enough time to do the measurement. Okay. Now, having chosen that, if I look at the change in pH or the change in H plus concentration per second as a function of tributylene concentration, right, then I get a fairly good linear plot, and I find that, so remember from this plot, the inset, I chose 1 minute as the time to ensure that it remains in the reactive phase and not saturated phase. And we can, from this plot, we can work out the sensitivity. So earlier, the sensitivity was given as U-bias per unit change in pH. This is the amount of H plus generated per second per millimolar of tributylene. We again use tributylene, but finally we'll use this standard plot and measure the triglycerides in the blood. Okay, so the rate of hydrolysis was given as 0.0481 per second per millimolar after 1 minute. The measurement has to be done after 1 minute of introducing the sample. How do I introduce the sample? I introduce the sample using a micro syringe, and here it shows it shows the change in real time. The star is the initial CV. After the sample is introduced, after 1 minute, the CV has shifted. Right, and in this we've also added the CV for calibration, those are two different measurements, one done at pH 6 and one done for pH 8.5. And the reason is the pH sensitivity, I told you, is 55 earlier, and it can be 59 is the theoretical limit. It can even become 45 if the surface somehow gets oxidized because of the ambience. So it's always important to do the calibration before doing the measurement. So the two data points for pH 6 and 8.5 is part of the measurement. First, the calibration is done, and this is included in the readout circuit. We just have to change the samples. After doing these two, you put the base sample and then add that is the buffer, and then add the triglyceride. Okay. So after using this protocol, let's look at the results. So again, we have compared with the clinical values that is measured in the patho lab, and these are our measured values, and you see there is more or less good agreement for all the samples. Now the question is, in the blood serum, we sometimes use dilution and sometimes we did not use dilution, right? So let me explain this. This is very important. I told you during the measurement of EIS cap that for small changes, the buffer which is present can cause the change in, can obliterate or cancel out the change in the pH if the pH change is small. That is, if the amount of triglyceride concentration is low. Now, if you look at the blood itself has buffer. Blood has buffering capacity. In fact, when they check blood, they always give what is the pH of the blood. It's, I think, 6.8 or something, very close to 7, but I think a little less than 7, right? So blood itself has a buffering capacity. Now what happens is, when I don't do dilution, no dilution, right, I get good matching between our value and the patho values. But the samples which we diluted with a buffer later, this is an additional buffer besides the buffer that is present in the blood. What happened is, these invariably had a higher triglyceride concentration. The moment the reaction started and the pH changed a lot, the blood buffer took over and overcorrected. So remember, in the CD plot, if you remember the plots, as more butyric acid got created, the curve shifted towards the left. And when we looked at the curves in real time, we found that it started shifting left and then it shifted right. And finally, when the reaction was completed, it was to the right, as if the reaction caused a change to make it more basic. Okay, and then we realized that was happening because of the buffering action of the blood. So that itself, if you have a shift in the other direction, that itself is an indicator that the triglyceride concentration is higher. So when you dilute that, what happens is that this additional buffer doesn't allow the blood buffer to play a role. So ideally, one should really dilute all the samples and do the measurement. But since we got away with the ones without dilution, this was an important point. Okay, now as you saw that we introduced the sample using a micropipette. Again, that means the operator interference can be there and errors can be there. So one possible, I just have a few slides on this, but it's very interesting. All of you would have heard of microfluidics. I think you have a lecture also in this talk on microfluidics, but that is traditional microfluidics using channels and valves and osmotic flow. What I'm talking here about is called as digital microfluidics. Okay, and we tried to develop a digital microfluidic platform for an EIS cap sensor. The advantage of digital microfluidic is you can have individual control of droplets, right? Microfluidic usually is continuous channel flow, whereas here we control it drop by drop. And the way it is designed, there's no evaporation because we use a 2-plate design. So it's covered on top by another plate. And so the evaporation is minimized. And so there was a lot of research going on for a few years. Actually, we didn't do much beyond this, but I just wanted to show it to you. And so this is a typical digital microfluidic 2-plate architecture. This is a side view. So what we have is two glass plates. On top is a ITO. ITO is a conducting oxide. So you can see there's a conducting material here. And below is another glass plate on which we have electrodes. This blue, red, blue, these are all electrodes. Typically, I think we've used chromium, right? And on top is a dielectric. We use silicon nitride. And both this kind of light brown color things is a coating which is Teflon-like. It could be Teflon or it could be some other coating which doesn't allow the drop to stick to the surface. So I have this Teflon. This is called as fouling since the droplet has lot of biological molecules in it. If they start sticking to the electrode, that is called as biofouling. We don't want that to happen. So everything is covered with a Teflon coating. If you look at the top view, this is what it looks like. Each of these blue is an electrode and they're connected outside to we'll apply the voltage here. So what you see is one of the electrodes is activated, that is voltage is applied, right? And so that is red, all the others are blue. What happens? It works on the principle of electrowetting, which is that if you have a droplet and you apply a voltage between the drop and the substrate, the contact angle will change. The drop can spread. In this case, the drop spreads. So therefore, I can do all these operations: splitting, transportation, cutting, merging, and dispensing. So what I would do is, again, this video doesn't work. What this shows here is the top glass plate, and this is the reservoir. Reservoir is just a large electrode. So I put a large drop here. And then by applying voltage in these electrodes, which are separated by a very thin gap, the drop moves here from one electrode to the other. The final, this square thing has a through hole, and the drop goes through the through hole and falls into the EIS cap, which is below. So this is the design. So remember, we already had used a glass packaging, right, on top for the silver chloride electrode. So this is my EIS cap. Now the top plate, I go ahead and put another plate on top of that and build a digital microfluidic array here, array of electrodes here. So I can start from the reservoir, which I am not showing in the picture, and by applying voltages to these electrodes, we can we can flatten out this drop by electrowetting and transfer this drop from electrode to electrode to finally come into here and do the measurement. So we showed that this works, and for a single EIS cap, it's not. I mean, you could even use a micro pipette. But if you, on the same dye, if you did glucose, urea, cholesterol, all these things, like a blood sample, we might want to test all this. So the sample is still the same, right? It's blood serum, but we could direct it to different EIS caps on the same dye using the microfluidics. Okay, so that covers the EIS cap part, and I'm at 4:41. I have time till 5. Okay, not much time. I don't think I'll get to the nanoporous membrane part. So that was the EIS cap biochemical sensor. Let me go to the micro cantilever now, which is a purely mechanical sensor. This is a schematic of a cantilever. As you can see, it's anchored at one end, fixed at one end, free to move to the other. Okay, and what you see on the surface is the immobilized molecules. Okay, so this is actually a platform. I can use this for antibody antigen system. I could use it for my triglyceride setup by immobilizing the enzyme on this, and so on. So here, then same schematic transducer, except the transducer now is mechanical, and I measure change in frequency. Now, the way it works is either because of this biomolecules attached to the beam can bend. And please note that the beam does not bend under the weight of this. It bends because whenever you put these additional molecules, it always has some stress. It generates some stress, and the bending is due to stress and not due to the weight. This is very important. Because of the stress, the beam bends. This is called as the static mode, or I could use the dynamic mode where it changes, the resonance frequency changes because of the mass. You know, the spring, the cantilever is like a spring, right? If I cause it If I actuate it just by hitting it on one side, it will resonate. If I do that close to its resonance frequency, it will keep vibrating till the damping kills it. The resonance frequency, simple harmonic oscillator, is typically given by square root of K by M, where K is the effective spring constant, which depends on the dimensions. Longer the beam, lower is the spring constant. Thicker is the beam, higher is the spring constant. And it also depends on the Young's modulus of the material. M is the effective mass of the cantilever. And there are a lot of applications of this as sensor for DNA, as an electronic nose to detect prostate cancer, pH sensing, and so on. Now, we wanted to use it for the triglyceride system, and how would we use it? So you remember the reaction. The enzymatic hydrolysis of tributylene created butyric acid and glycerol. So far for the EIS cap, we were concentrating on the formation of acid. But let's look at the glycerol now. Glycerol is a dense and viscous liquid. So if I introduce the cantilever beam in this I don't need an electrolyte now, right? Because I'm not doing a electronic measurement. I'm not measuring capacitance. I don't need a conducting liquid. I need an insulating material. So the liquid is insulating, usually deionized water, to which we add the bioanalyte, and the enzyme is immobilized on the surface of the cantilever beam. As the reaction takes place, more and more glycerol gets formed. So what will happen? The mass changes, and therefore the resonance frequency. Look at the previous slide. This is the amplitude as a function of frequency. If the mass increases, resonance frequency will decrease, right? Because it's 1 upon square root of M. If the mass reduces, it will move to the right. So the resonance frequency reduces as more and more glycerol gets formed. So in here, towards the left, you see resonance frequency as a function of time. And that's exactly what you see. As the reaction proceeds and more glycerol gets formed, the resonance frequency reduces because glycerol is much more massive. It's more density. And of course, it saturates towards the end. After half an hour, reaction is over because all the bioanalyte in the adjoining liquid has now reacted, and therefore no more glycerol is getting produced. So again, we created first a calibration plot. This is a resonance frequency as a function of, I moved it somehow, as a function of concentration. The way we created the plot, the calibration plot, was mixing glycerol and butyric acid separately, because we know how much butyric acid and how much glycerol gets created, and we measured the resonance frequency as a function of that concentration, and then we did the actual sample. The blacks are the actual tributylene getting hydrolyzed, and you see it agrees very well. So resonance frequency changed from 47 to 36.8 kilohertz for 10 to 100 micromolar. So already the lower range has reduced by an order of magnitude simply because we are not using a buffer. So when I first saw this many years back, this is work of a student published in 2009, really long back. So I always thought electronics is most sensitive. So this was a learning experience to find mechanical sensors can have higher sensitivity than electronic sensors. Okay, now this is a plot which gives the sensitivity, mass sensitivity of resonant devices as a function of year. And, fantastic sensitivities have been achieved with this. Here, this is attogram is 10 minus 18. So even 10 minus 20 has been achieved. This is in 2010. Zeptogram has been achieved now. And as of 2020, this number is at zeptogram. Okay, which is 10 minus 21 or something is zeptogram. But if you look at these plots, they're in different colors. The ones in red are in vacuum, the ones in green are in air, and the ones in blue are in liquid. And as expected, the red ones are the best. Why as expected? Because what will kill the sensitivity? If for a resonating beam, what causes it to stop? It is the damping. So the damping will be the least in vacuum and will be highest in liquid. So even though this record sensitivities were obtained in vacuum, that is not so useful for biosensing, simply because all our biological samples will be in liquid. So that's what we try to do next, how to improve the sensitivity in liquid. So this is an example of the same cantilever, our cantilever, measured in air and in water. And you can see, look at the plot here. Of course, there's a shift because of the mass of the water. But besides that, look at the signal. It's so much smaller than in air. Why? Because of the damping. It's a lossy signal. Also, the full width at half minima or the Q factor also gets worse when you measure in liquid. So what is the solution? How do I do measurements in liquid with high sensitivity? There are two factors to be discussed here. For, of course, damping I just mentioned. There's also something called as hydrodynamic loading. And usually people who work with ships talk about hydrodynamic loading. What is that? So if I have a resonant cantilever, it is moving in the liquid. There is damping force, of course, coming from the liquid. But not that. As the beam moves in the liquid, it's generating waves or some movement in the liquid, and that itself is loading the cantilever. So damping and hydrodynamic loading are two different aspects. The hydrodynamic loading comes because of the interaction of the liquid due to the movement of the beam. Now, there's since it comes from ships, etc., there's always already a lot of work in that. What is found is that when we work in higher resonance modes, right? So the previous results I showed you were all the first excitation mode. If you go to higher modes, then both damping as well as the effect of hydrodynamic loading goes down. So this plot on top shows theoretically how the hydrodynamic function falls as the mode decreases. So from first mode to 14 mode, it has gone down from 1 to about 0.4. Okay, and it is also found that at higher modes, the damping is also much less. And you can understand that. See, when the beam is moving very fast, the liquid is a slow mover. Liquid doesn't even register that the beam is moving so fast. So it's as if the damping, we can overcome the damping and the hydrodynamic loading simply by working at higher frequency modes. So we worked with two systems. One was bought. It is a custom-made system called CantiSense, bought from Germany. And here the advantage was that the measurement could be done while the liquid was flowing. Well, that's what we thought, but we found that when the liquid was moving, again, it affected the sensitivity. And it uses a laser and a position-sensitive detector to find the shift in the resonance frequency. We also used a Doppler vibrometer. That is what is normally used for measuring resonance frequency in MEMS labs. But since we wanted to measure in liquid, we designed something like this, where we would, of course, everything is very important here, amount of liquid, volume, etc., how you fix the cantilever array. So that's how we compared the measurements in liquid using both the vibrometer as well as the CantiSense. So let's first just do a frequency sweep to see all the modes. The first problem is that you have to identify the modes. If I want to use the formula, I have to say this is the 8th mode or this is the 10th mode. As it turned out, there were more number of peaks than the number of modes. So first you have to remove all the spurious modes. Where do the spurious modes come from? We found that they can come from the way the cantilever is held at the support, right? It can come if the spot size of the laser is too large, that it covers multiple modes at the same time. So all those various errors had to be removed. And one simple way of doing that is to plot the difference mode as a function of mode number, and it should be monotonically increasing. Anything that veers away from it is a spurious mode and should not be taken into account for the calculations. We also worked it on in a dynamic mode. I mean, both are dynamic mode in the resonance mode, but this is phase locked loop. The first one is frequency sweep. So we just swept through all the frequencies and picked out all the modes. Here we decided whichever mode has the highest amplitude, right? And then at that mode we locked the phase and did the measurement. So as you can see here, at this point the water is introduced and there's a peak in the signal, and then it kind of stabilizes, then the water is taken out, and this is a bad signal because it should come back to this value. The baseline has changed. So a lot of parameters have to be adjusted. This is good because it has come back to the same value. And phase locked loop can also be used. Best signal to noise ratio we got at the 14th mode. And actually this turned out to give better sensitivity. The minimum measurement was 100 picogram. However, we found with the combination of measurements in air and in liquid gave us the best results. Measurements in air are very clean. You have no spurious mode, very lovely sharp peaks, and you can see the frequency as a function of mode number follows theory exactly. What we use this for is to determine what the Young's modulus is. Because these are thin films, we use polysilicon cantilevers. The Young's modulus can vary depending on deposition conditions. So you can't use silicon is constant. Polysilicon, it can depend depending on the conditions. So we measured the Young's modulus by fitting the plots measured in air. We also measured the dimensions exactly using a scanning electron microscope, right? And we used all these values, Young's modulus, etc., to put that in the measurement in liquid and then got the sensitivity or the delta F value. If you don't have two different, the LDV, the Doppler vibrometer to do measurements in air, one can just do a very large number of measurements and do a Monte Carlo optimization so that the errors get removed. And that also gave us a fairly good delta F by delta M. Of course, method 2 was better, but both are possible. So what did we get? With in-house fabricated polysilicon cantilevers of micrometer sizes, 3 micron thickness and 200 micron length, 20 micron width, the triglyceride detection could be brought down to 50 micromolar, right? Earlier was 10 millimolar. So we brought it down by several orders of magnitude. We also used the same setup for antibody antigen, and we could measure 1.5 nanogram and 14 picogram using vibrometer. We used the setup to measure a TB biomarker, IFN gamma. We never reported these results because we could not get clinical verification for these. And as well as cholera toxin, which also could be measured in nanograms. So in principle, when you have very small samples, cantilever would be a good way to go to measure this, the quantity. However, actually our original interest in going to such low concentrations was because we wanted to measure virus. You know, meningitis is caused by a virus and they have to do this culture, PCR, to detect the virus. And by the time that PCR culture happens, the disease is already quite advanced. So we were talking to a virologist in CMC and we thought if you can use the cantilever, we can measure even the presence of a few virus-based femtogram, and we are still in picogram. That's how it started. So we thought if you reduce the dimensions of the cantilever beam, of course, because it's square root of k by m, if you reduce the dimensions, m will reduce and sensitivity is going to go up because sensitivity depends on the higher the resonance frequency, higher is the sensitivity. But it's kind of, there's a trade-off. If I make the cantilever beam too small, chances of it catching a virus, that the virus will come and settle on the cantilever, also reduces. So that's the reason we didn't change the length and the width too much. That remained in micrometers. What we changed was the thickness to 1. Both combination of bulk and surface micromachining. This is a process developed by us, and we made these cantilevers. You can see this end part, the projection is what the nano cantilever is. And we measured using this, the triglyceride concentration, the change in delta F as a function of tributary concentration, and we could bring down the detection of triglycerides to 10 nanometer. Again, antibody antigen came down to 409 femtogram. In bracket are the values that the best values we got with our larger cantilevers. So this is a much greater improvement compared to earlier. It is still in hundreds of femtograms. But then again, when you want to measure virus, it won't be one virus. So now in principle, we should be able to measure it. But we are not doing that work anymore. This is the last one that we did. I'm going to skip this because I've already hit 5. And I just wanted to show you 2-3 slides on nanoporous membrane. We do use MEMS technology, though it's not a MEMS sensor or an actuator. It's a passive device. But to make the nanoporous membrane, we use MEMS technology. What is the use of nanoporous membrane? What defines a nanoporous membrane? That the pores should be nanometer size. And because of this nanometer size pore, this is a schematic of filtering, or what is called as a dialysis unit. Dialysis is not necessarily hemodialysis. There's a difference between dialysis and filtering. In filtering, you will keep everything above a certain size away. It's perfect. When I filter my tea, only the tea comes out, not a single tea leaf goes through. In dialysis, it can be a range, right? Within a range, above that range, things will not pass. Below that range, everything will pass. Okay. So usually these membranes are made of polymer materials, biological membranes and things like that. But if you make it out of silicon, the membranes are very thin. They are 15 nanometers thin. If the membranes are made of polymers, they are so thick that sometimes the molecule itself gets stuck in that hole through the pore. So if you use very thin membranes, then the throughput increases and it's very easy. Clogging is usually much less. So we made silicon nanoporous membranes, and we micromachined 5 micron of silicon first, deposited oxide, amorphous silicon, and again oxide by PCVD technique. And you can see that the amorphous silicon layer is just 15 nanometers. And then when it goes through a rapid thermal processing, the silicon tries to form crystals. And because it's a thin film, there isn't enough material, so spontaneously pores form. So that is the beauty of this. It's again a batch process, and I can form very thin, 15 nanometer thin nanoporous membranes using a batch process. This is a transmission electron microscope picture. These white dots that you see, those are the pores. The gray is the amorphous silicon, and the black is what has crystallized. If you look at the pores, they're not circular, they're more like ellipses. So we define them by a major and a minor diameter. And you can see that the distribution is actually quite tight. Major diameter is about 10 nanometers, 10 to 12 nanometers. Minor is about 8 is the maximum, 8 nanometer, average is 8.17. So I get a tight distribution of pores. And this allows to pass, this will sometimes, and also the surfaces of the pores are charged. You have to look at all that also. It allows things to diffuse. Okay, we will not spend time in that. We found that even though there may be some large pore size, it's actually very good. It doesn't allow any bacteria or yeast to go through it, right? Of course, bacteria is much larger size, but because there's a distribution of pores, it's possible that there may be 1 or 2 large pores. But this, we have done a culture, which is a few days, and even if 1 bacteria or 1 yeast cell had passed, we would have seen it. It's not seen. So it is proof of this. We also did this for virus, which is much smaller, for polio virus, which is 30 nanometer, and influenza virus, which is bigger, and our nanoporous membranes with average 10 nanometer pores didn't allow either of these viruses to go through. So we are now working with these membranes to check, to see if it will work for hemodialysis, kidney, to remove the uremic toxins. And we find actually they can clear urea as well as creatinine, 80% clearance of urea and 90% clearance of creatinine. This is just a lab-based system, Teflon cell, and so the blood serum or the mock fluid is coming on one side, and the buffer is coming on the other side, and all the uremic toxins transfer and the blood flows back. This is the principle of the measurement. Of course, if you use a single membrane, it's going to take ages to do to get any competitive numbers. So we are now making arrays. So you have multiple nanoporous membranes, 3 by 3, even bigger than that. This is a full 4-inch wafer with different array distributions. And we found that we can handle, I think, volumes up to 50 milliliters now in 1 hour. And the clearance numbers are also very good. Okay, I'm going to skip all this. If you want, I can send you my slides. These are work from somewhere else, just to give you an idea of the MEMS area, but I think we have more talks on bio-MEMS also. So my collaborator for many years from the Department of Biotechnology was Professor Anju Chadha. Shanti Pawan helped with the circuits. Anil helps me with all my data analysis, etc. We had several postdocs. We still have some of them, and many students working on this. This is work of, I don't know, started I think in 97. The first EISCAP we made was in 97 with funding from various agencies. So thank you very much for listening to me, and I welcome questions now.
Since the forum is open for discussion, please have the questions. If any questions are there, please have.
Oh, thank you. There's a lot of good things being said in the chat. Thank you. No questions. Has everyone fallen asleep? I want one question.
Good evening, ma'am.
Good evening.
Madam?
Yes, hello.
Madam, electrode optimization, suppose I want welding electrode, how to optimize the electrode optimization? Welding electrode?
Silver chloride.
Yeah.
So silver chloride is actually very simple to make. You can, if you are going to use a wire, you can just take a silver wire, dip it in hydrochloric acid, and it forms silver chloride. Okay, but for us it was thin film, so we deposited silver. Silver doesn't stick very well to glass, so we had to use chrome and then gold, and then deposit silver on that by evaporation, and then we exposed it to actually it was not hydrochloric acid directly. I can't remember, some compound containing chlorine, and that made it silver, the top surface as silver chloride. What happens is if you keep using it, the silver chloride layer goes off. So you have to again redo it. But as biosensors, people don't want to reuse biosensors. In the lab, we keep reusing them. But in field, I think they're afraid of cross-contamination. Nobody wants to reuse. So then it's fine. You know, if you use it a few times, there'll be no problem with the electrode.
Okay. And in other, this copper electrode, in the electrolytic condition?
We have not used copper electrode for anything. Copper electrode where?
In electrolytic condition?
No, the other electrode is aluminium deposited on silicon.
Okay.
That doesn't get exposed to the electrolyte at all. So that is very stable. That is standard.
Okay.
Yeah.
Thank you, madam.
Welcome.
Good evening, ma'am. I'm audible.
Hello. Yes, you're audible.
Yeah, ma'am. Thank you, ma'am, so much, first of all, for wonderful presentation. My question is that I'm also working with this cantilever technology, actually, as you said, the paper-based technology. So I have just question that when we are making this, the conductive ink for the when passing the reactions, and because we have to use that some kind of a nitrocellulose paper to get the conductivity, because the smudging is happening between if you make some like a paper-like based cantilever, ma'am. So how we can get to know that, how we can avoid this kind of situation, ma'am?
I think you have to use some coating.
Okay,
if you
ma'am.
look at literature, you'll find that there are coatings, because I think Whitehead is the one who introduced paper-based sensors, and so that is where the chemistry, biochemistry, etc. comes. You have to use a coating which will not let it smudge, but it should not interfere with the measurement. So there's a lot of optimization involved there. Yes.
Yes, ma'am.
So I did not mention this. I was talking mainly about silicon sensors, but a lot of polymer cantilevers are also used. I think IIT Bombay did a lot of work, and tomorrow you'll probably hear from your nanoscience talk. Polymers are inexpensive, so for use and throw it's very good. But for very accurate measurements, nothing beats silicon. Yeah.
Yes, ma'am. Because as like you mentioned that now POC devices just all coming like use and throw devices or lateral flow assays coming like that, and we have to I think how we can get that like a very cheap material, because all these materials are very expensive, right? For example, silver chloride or the silicon base, it will be expensive. So how we can make some kind of a cheap material, ma'am? So
Yeah, but finally, it can't be just cheap, right? Because it also has to be reproducible. It has to be reliable, right? Unless it is reliable, the problem with polymer also is it has a habit of swelling. Even
Yes,
with,
ma'am.
ambient water vapor, it can swell. So then the packaging has to be very good, so that it
Yes,
doesn't do that. So there's always a trade-off. Polymers, of course, are much less expensive than silicon, but everything has its plus and minus.
yes, ma'am. Okay, thank you, ma'am.
So I got two questions. I asked one and I got at least two. So now I should let you go. Right?
Ma'am, we have vote of thanks. Stay for a minute. So
Okay.
I request Dr. Ankit Oza to give vote of thanks.
Hello, good afternoon, ma'am.
Yes. Hello.
Thank you for your in-depth and very such nice lecture on BioMEMS and its applications. So, first, on behalf of all the participants and the university, I would like to give us some brief about your introduction talk. So first you touched about the various silicon-based biosensors, and then you have discussed importance of tribological detection techniques in depth. And I hope all of us get a very good, excellent knowledge in that fabrication of tribology detection technology. And furthermore, you have extended your talk with electrolyte insulator semiconductor capacitor. So, along with the EISCAP fabrication process briefly, and then you discuss about in depth of thin film argon AgCl for integrated biosensors applications. So in that we got also knowledge about this process of AgCl process, and madam also spoke about the what she has developed in that readout circuits in their laboratory at IIT Madras, and gave different advantages and real time applications of integration of digital microfluidics with EISAB applications. Furthermore, in the last session, in the last time talk, micro cantilevers with their applications along with the nano porous membranes for various biological and applications. So, would like to thank Ishanki madam, and definitely we would like to continue with our research work with the collaborative type with IIT Madras and especially with you. So thank you once again, ma'am, Ishanki ma'am.
Thank you. So I can see many people are asking for sharing of the talks. I have no problem. I can share, but it's too long. So we have to figure out a way of transferring it. So please let me know. Email me and I'll do that. Okay.
Yes, sir. You can mail me. I'm Dr.
No, I'm not sure it will go by mail because
by drive can it go?
Yeah, I'll try that. If it goes by mail, fine. Otherwise, I can also cut down a few things.
Yeah, you can. And then you can share. Then I can share with all the participants.
Okay, I'll do that. Okay, thank you, everybody.
Thank you, madam. Thank you very much.
Thank you, madam. Thank you very much.
Thank you, madam. Sir, is there any link, sir, feedback?
Yeah, I will share in a group, WhatsApp group.